Let me draw a good old PV diagram. That's my pressure axis. This is my volume axis. Just like that, I have pressure and volume. I showed several videos ago that if we start at some state here in the PV diagram, right there, and that I change the pressure and the volume to get to another state, and I do it in a quasi-static way, so essentially I'm always close to equilibrium, so my state variables are always defined. I could have some path that takes me to some other state right there. And this is my path. I'm going from this state to that state. And we show that if I just did this, the work done by the system is the area under this curve. And then if I were to move back to the previous state, and then if I were, by some path, just some random path that I happen to be drawing, the work done to the system would be the area under this light blue curve. So the net work done by the system ended up being the area inside of this path. So this is, let me do it in a different color. The net work done would be the area inside of this path when I go in this clockwise type of direction. So this is the work, the net work. Let me write net work done by system. Done by system. Done by the system. And now we also know, we also know that if we're at some point on this PV diagram, that our state is the same as it was before. So if we go all the way here and then go all the way back, all of our state variables will not have changed. Our pressure is the same as it was before. Our volume was the same as it was before, because we went all the way back to that same point on the PV diagram. And our internal energy is also the same point as it was before. So our change in internal energy over this path, you're going to have a different internal energy here than you had here. But when you go around the circle and you get back, your change in internal energy is equal to 0. And we know that our change in internal energy, it's defined as, and this is from the first law of thermodynamics, the heat added to the system. So it's the heat added to the system minus the work done by the system. Now, if we go on a closed loop on our PV diagram, then what's our change in internal energy? It's 0. So we get 0 change in internal energy, because we're at the same state, is equal to the heat applied to the system minus the work done. Or, and I've done this little exercise multiple times. I think this is probably the 4th or 5th time I'm doing it. We get that the heat added to the system, if we just add W to both sides, is equal to the work done by the system. So this area under this, inside of this path, I already said it's the work done by the system. And if you don't remember even where that came from, it was, remember, pressure times volume times change in volume is a little incremental change in work, and that's why it relates to the area. But we've done that multiple times. I won't go there just yet. But so if you have any area here, some heat was added to the system, some net heat. Right? Some heat was added here, and some heat was probably taken out here. But you have some net heat that's added to the system. And I use that argument to say why heat isn't a good state variable. Because, and I had a whole video on this, that if I define some state variable, let's just say heat content. Let's say I wanted to define some state variable, heat content. And I would say that the change in heat content would, of course, be equal to the change in heat. And that's what I'm defining. If I'm adding heat to the system, my heat content should go up. But the problem with that heat content state variable was that, let's say over here, I say that the heat content, let's say that the heat content is equal to 5. Now, I just showed you that if we go on some path here and we come back, and there's some area in this little path that I took, that some heat was added. So let's say that this area, and let's say that this area right here, so this is Q, is equal to the work done by the system. Let's say it's equal to 2. So every time, if I start at heat content is equal to 5, that's just an arbitrary number, and I were to do this entire path, when I go back, the heat content would have to be 7. And then when I go back and do it again, my heat content would have to be 9. And it would have to increment by 2 every time I do this exact path. It would have to increment by the amount of area that this path goes around. So heat content can't be a state variable because it's dependent on how you got there. A state variable, and remember this, in order to be a state variable, if you're at this point, you have to have the same value. If your internal energy was 10 here, when you do the path and you come back, your internal energy will be 10 again. That's why internal energy is a valid state variable. It's dependent only on your state. If your entropy was 50 here, when you go back and you do all sorts of crazy things and you come back to this point, your entropy is once again 50. If your pressure here is, I don't know, if it's 5 atmospheres, when you come back here, your pressure will be 5 atmospheres. Your state variable cannot change based on what path you took. If you're at a certain state, that's all that matters to the state variable. Now, this heat content didn't work. And that's why we actually led into some videos where I divided it by T and we got entropy, which was an interesting variation. But that's still not satisfying. What if we really wanted to develop something that could in some way be a state variable, but at the same time measure heat? So obviously we're going to have to make some compromises, because if we just do a very arbitrary kind of heat content variable, then every time you go around this, it's going to change, so it's not a valid state variable. So let's see if we can make up one. So let's just make up a definition. Let's call my new thing that I'm going to try to maybe approximate heat. Let's call it H. And just as a little bit of a preview, we're going to call it enthalpy. Enthalpy. And let's just define it. I'm just playing around. Let's just define it as the internal energy plus my pressure times my volume plus pressure times volume. So then what would my change, what would be my change in enthalpy be? So my change in enthalpy will be, of course, the change of these things. But I could just say that's my change in my internal energy plus my change in pressure times volume. Now this is interesting, and I want to make a point here. This, by definition, is a valid state variable. Why is it? Because it's the addition of other state variables. Right? At any point in my PV diagram, and it's also true if I did diagrams that were entropy and temperature or anything that dealt with state variables, at any point on my diagram, U is going to be the same no matter how I got there. P is, by definition, going to be the same. That's why it's at that point. V is definitely going to be the same point. So if I just add them up, this is a valid state variable because it's just a sum of a bunch of other valid state variables. So let's see if we can somehow relate this thing that we've already established as a valid state variable from the get-go, from our definition. This works because it's just a sum of completely valid state variables. So let's see if we can relate this somehow to heat. So we know what delta U is from one of, it's if we're dealing with all of the internal energy or the change in internal energy, and I'm not going to deal with all the other chemical potentials and all of that. It's equal to the heat applied to the system, minus the work done by the system, right? And let me put everything else there. The change in enthalpy is equal to the heat applied minus the work done. That's just the change in internal energy. And plus delta PV. This is just from the definition of my enthalpy. Now this is starting to look interesting. What's the work done by a system? What's the work done by a system? So I could write change in H, or enthalpy, is equal to the heat applied to the system minus what's the work done by a system? If I have some system here, it's got some piston on it. If we're doing it in quasi-static, I have the classic pebbles that I've talked about in multiple videos. When I apply heat, or when let's say I remove some of these pebbles, so I'm at a different equilibrium. But what's actually happening? When is the work being done? You have some pressure being applied up here, and this piston is going to be moving up, and your volume is going to increase. And we showed multiple videos ago that the work done by the system can be, and you can kind of view this as the volume expansion work, it's equal to pressure, pressure times change in volume, and then let's add the other part. So this was our change in internal energy, and I had several videos where I show this. And now let me add the other part of the equation. So our enthalpy, our change in enthalpy, can be defined by this. Now something interesting is going on. I said that I wanted to define something because I wanted to somehow measure heat content. My change in enthalpy will be equal to the heat added to the system if these last two terms cancel out. If I can somehow get these last two terms to cancel out, then my change in enthalpy will be equal to this, if somehow these are equal to each other. So under what conditions? Under what conditions are these equal to each other? Or another way, under what conditions is delta pressure times volume equal to pressure times delta volume? When does this happen? When can I make this statement? Because if I can make this statement, then these two terms are equivalent right here, and then my change in enthalpy will be equal to the heat added. Well, the only way I can make this statement is if pressure is constant. If pressure is constant. Constant pressure. Now, why is that? Let's just think about it mathematically. If this is a constant, then if I just change, if this is just 5 times the change in something is the same thing as a change in 5 times that thing. So it just mathematically works out. Or if you view it another way, if this is a constant, you can just factor it out, right? I mean, you could just say, if I said the change in 5x, that would be, you could say that's equal to 5 times x final minus 5 times x initial. And you could say, well, that's just equal to 5 times x final minus x initial. Well, that's just equal to 5 times the change in x. It's kind of almost too obvious for me to explain. I think this, sometimes when you over-explain things, it might become more confusing. So this applies, and the 5 I'm just doing is the analogy for a constant. So if pressure is constant, then this equation is true. So if pressure is constant, so this is a key assumption, then, so if we have, if heat is being applied in a constant pressure system, so we could write it this way. So I'll write it multiple times because this is key. If pressure is constant, then our definition, our little thing we made up, this enthalpy thing, which we defined as internal energy plus pressure and volume, then in a constant pressure system, our change in enthalpy, we just showed, will be equal to the heat added to the system, because all of these two things become equivalent under constant pressure. So I should write that. This is only true when heat is added in a constant pressure system. So how does this gel with what we did up here on our PV diagram? What's happening in a constant pressure system? Let me draw our PV diagram. That's P. That's V. Let me make sure I'm right there. This is P, and this is V. So what's happening in constant pressure? We're at some pressure right there. So if we're under constant pressure, that means we can only move along this line. So we could go from here to there and back to there, or we could go from there to there, back to there. So we could go there all the way there and then go back. But what do we see about this? Is there any area in this curve? I mean, there is no curve to speak of because we're staying in a constant pressure. We've kind of squeezed out this diagram. We've made the forward paths and the return paths the same exact path. So because of this, you don't have that state problem, right? Because no net heat is being added to the system when you go from this point all the way to this point and then back to this point. So because of that, you can kind of see visually that enthalpy in a constant pressure, when you're not moving up and down in pressure, is the same thing as heat added. So you might say, hey, Sal, this was a bit of a compromise, constant pressure. That's a big assumption to make. Why is this useful at all? Well, it's useful because most chemical reactions, especially ones that occur in an open beaker or that might occur at sea level, and that should be a big clue, they occur at constant pressure. If I'm sitting at the beach and I have my chemistry set and I have some beaker of something and I'm throwing other stuff into it and I'm looking for a reaction or something, it's a constant pressure system. This is going to be atmospheric pressure, 1 atmosphere. I'm sitting at sea level. So this is actually very useful. This is a very useful concept for everyday chemical experiments. It might not be so useful for engines because engines always have pressure changing, but it's very useful for actual chemistry, for actually dealing with what's going to happen to a reaction at a constant pressure. So what we're going to see is that this enthalpy, you can kind of view it as the heat content when pressure is constant. In fact, it is the heat content when pressure is constant. So somehow we were, well, not somehow, I showed you how. we were able to make this definition, which by definition was a state variable because it was the sum of other state variables. And if we just make that one assumption of constant pressure, it all of a sudden reduces to the heat content of that system. So we'll talk more in the future of measuring enthalpy, but you just have to say if it's pressure is constant, enthalpy is the same thing as, and it's really only useful when we're dealing with constant pressure, but if we have pressure constant, enthalpy can be imagined as heat content, and it's very useful for understanding whether chemical reactions need heat to occur or whether they release heat, so on and so forth. See you soon.